Hi, today we are going to discuss Principle of Induction. This is a continuation of our discussion about the set of integers. So for this video, we're going to discuss two versions of induction, the weak version and the strong version. We are also going to discuss the first principle and the second principle of mathematical induction. So if you're ready, alina't matuto. So let's start with weak induction. So let S be a set of positive integers satisfying the following. 1 is in S, and if a positive integer k is in S, then k plus 1 is also in S. Then we conclude that S is actually the set of natural numbers. So we prove this by contradiction. Suppose S is not the set of natural numbers. Then we should be able to find a contradiction. So if we suppose that S is not the set of natural numbers, then of course S does not contain the whole set of natural numbers. So what does it mean? It means that there's an element of the set of natural numbers which is not in S. So let's collect all of those elements and let's call it T. So let T be the set containing all natural numbers that are not in S. Now, take note that T is not empty, yes. Because if T is empty, then all X is in S. But S is not the set of natural numbers. So there must be an element of the set of natural numbers which is not in S. And that element is in T. So T must have at least one element. So it's a non-empty subset of positive integers. Right? So by the well-ordering principle, T must possess a least element. So the well-ordering principle would imply that T has a least element. So let's say this least element is M. In terms of our set T, M is the smallest. So any element in T is either equal to M or M smaller than that element. By condition 1, since 1 is in S, this necessarily means that M cannot be 1. Right? Okay. So again, the elements of T are those that are not in S. So if a natural number is in S, then it cannot be in T. So since we assume that 1 is in S, then 1 is not in T. So what does it mean? Naturally, it means that M is greater than or equal to 2. Right? So M should be greater than 1. Okay. So it follows that M minus 1 is positive. Right? This should imply that M minus 1 is greater than 0. But of course, since M is an integer, M minus 1 is definitely less than M. Since M is the least element in T, right? M is the smallest. Remember, this is the smallest. This is the least. So anything smaller than M cannot be in T. So that means M minus 1 must be in S. Right? Because, again, by construction, anything that is not in S is in T. So anything not in T is in S. So by condition 2, if an integer is in S, then that integer plus 1 is also in S. So that means M minus 1 plus 1, right? which is just the same as M, must also be in S. So we have a contradiction here. So M is in T and M is in S. That's a contradiction because T and S contains no common element. Kasi by construction, whatever is not in S is in T. So whatever in T cannot be in S. Alright. So since we have a contradiction, then that assumption is false. Therefore, S is indeed the set of natural numbers. Okay? In simple terms, the weak version of the induction means that if you have a set containing 1, the second assumption says that if you have an integer, then the next integer is also in S. Since 1 is in S, then by second assumption, 2 will be in S. Now again, using the second assumption, since 2 is in S, then the next integer, which is 3, will be in S. Now, since 3 is in S, then the next integer, which is 4, is also in S, and so on and so forth. So, that's what the induction means. So, inductively, once you say that 1 is an element of S, the second assumption ensures us that all the integers will also be in S. So that means S is the same as the set of natural numbers. So how do you use this form of induction to establish or to show mathematical properties? So let's have an example. Here is an example. We want to show that 1 squared plus 2 squared plus 3 squared and so on up to n squared is equal to n times 2n plus 1 times n plus 1 all over 6 for all n greater than or equal to 1. So what we're going to do is we want to create a set S containing all natural numbers satisfying this equation. So let S be the set containing all natural number such that n satisfy equation 1. Now, in order to show that the formula holds, using induction, we need to show two things. First, that 1 is in S. And second, if k satisfy the equation or if k is an integer that satisfy the equation, then we must show that k plus 1 also satisfy the equation. So let's do the first step. So for n equals 1, so the left hand side is equal to 1 squared, which is 1. On the other hand, the right hand side is equal to 1 times 3 times 2 all over 6, which is also equal to 1. So this tells us that 1 satisfy equation 1. So 1 is indeed in S. For the second part, we want to assume that K is in S. In other words, that means K satisfy equation 1 or 1 squared plus 2 squared plus 3 squared and so on up to K squared is equal to K 2K plus 1 K plus 1 all over 6. So we just substitute K in our equation 1. All right. Now, what we want to show, so we want to show that k plus 1 is also in S. So what does it mean for k plus 1 to be in S? That means k plus 1 also satisfy equation 1, or that is 1 squared plus 2 squared plus 3 squared and so on plus k squared this time up to k plus 1 squared must be equal to k plus 1 quantity 2k plus 1 plus 1 then quantity k plus 1 plus 1 all over 6. Or if we simplify, we have k plus 1 times the quantity 2k plus 3, k plus 2 all over 6. So we want to show that this equation holds. Now, so in order to show equality, we want to show that the left-hand side is equal to the right-hand side. So we start with the left-hand side. The left-hand side is equal to 1 squared plus 2 squared plus 3 squared and so on plus k squared plus k plus 1 squared. So that's our left-hand side. Now, using our assumption that k is in S, that means we can simplify this using our formula. So that's equal to k times 2k plus 1 times k plus 1 all over 6. And then we rewrite k plus 1 quantity squared. So using algebraic manipulation, we can combine this as a single fraction all over 6. So we have k, 2k plus 1, k plus 1 plus 6 times k plus 1 squared. Take note that k plus 1 is a common factor. So we can factor that out. So we can factor k plus 1, right? And we're left with k times 2k plus 1, right? Plus 6 quantity k plus 1. All right, all over 6. So if we simplify the second factor, so we have 2k squared plus k plus 6k plus 6 all over 6. So that's equal to k plus 1 times 2k squared plus 7k plus 6 all over 6. Now, observe that the second factor is factorable, right? So we can factor that as 2k, k, and the factor of 6 is either 1 times 6 or 2 times 3. So let's take 2 and 3. So I put here 3 and 2. So to check if that indeed is the same as our original expression. So 2 times 2k times 2, that's 4k, right? And 3k is 3k. 3 times k is 3k. So 3k plus 4k is indeed 7k. So that means we have the right combination. So we have 2k plus 3, k plus 2 all over 6. But this is precisely what we want to show. That's already the right-hand side. So indeed, this is equal to the right-hand side. So what does this tells us? So this tells us that k plus 1 is indeed in S. So we're able to show two things. First, that 1 is in S. And second, whenever we assume that k is in S, so we assume k in S, we were able to show that k plus 1 is also in S. So using the weak induction, we can now imply that S is the set of natural numbers. Or that means, in terms of our representation of X, equation 1 holds for all natural number n. And we are done. Recap, we showed two things. First, we showed that number one, the element 1 is in S. And number 2, we assume that K is in S. We show that K plus 1 is in S. So once we've shown these two, we can therefore conclude that S is the same as the set of natural numbers. The first item, 1 is in S, is called the basis of induction. And the second one is called the induction step. In our induction step, the assumption that K is in S is called the hypothesis or the inductive hypothesis. So using induction is always two steps. First, we show the basis of induction. So that means you must be able to find a starting element in the weak form of the induction. The starting element is 1. And then you need to show the inductive step. So the inductive step tells us that starting from 1, every succeeding integer is also in S. So that means if there is an element k in S, then we must be able to show that the next integer k plus 1 is also in S. Now, both of these assumptions are important. And both of them must be satisfied for induction to work. So for example, if we ignore one of the steps, so let's say we have the equation 1 plus 3 plus 5 plus and so on up to 2n minus 1 equals n squared plus 3. So if we try to bypass the basis of induction and proceed directly to the inductive step, so let's say we automatically assume that k is in S, right? So we're here again, S is the set of all integers satisfying this equation. So let's call this equation 2. So let's say S is all the integer such that equation 2 holds. And we went straight away to assume that K is in S. So if K is in S, then that would necessarily mean that 1 plus 3 plus 5 and so on up to 2n minus 1 is equal to n squared plus 3. So what does this tells us? This tells us that if we add another integer, 1 plus 3 plus 5, so these are the sum of the odd integers. So the next odd integer is 2n plus 2. So that's just equal to the first group is equal to n squared plus 3, right? And then plus 2n plus 2. Well, but this is equal to n squared plus 2n plus, sorry, this should be plus 1. Plus 1. So this is plus 1. Okay. So what I'm going to do is I will keep plus 1 on n squared plus 2n and I will split 3 on the other side. Why? Because n squared plus n plus 1 is the same as n plus 1 squared plus 3. So this tells us that n plus 1 also satisfy equation 2 or that n plus 1 is in S. Right? And we may at this point conclude that the formula holds. But take a look at the value n equals 1. At n equals 1, so we have on the left hand side equals 1 and on the right hand side that's equal to 1 plus 3 which is 4. And obviously they are not equal. Actually, even if we test n equals 2, let's say n equals 2, so we have 1 for the left hand side, 1 plus 3. On the other hand, the right hand side is equal to 2 squared plus 3 or that's equal to 7. So obviously 4 is not the same as 7. So although we were able to show that the inductive hypothesis is satisfied because we failed to on the first place show the basis of induction. So on the first place mali naman pala yung equation. So that means the proof failed because we failed to address the basis of induction. So induction involves two things. You prove the basis of induction and then you prove the induction step. So whenever the two are true, then we can always assume that the property holds for all natural number and greater than or equal to 1. Now, it doesn't necessarily mean that we should always start with 1. Sometimes equations or a certain formula is not true for the first k integers, but after some point it will be true starting from that certain initial value n sub 0. So we can generalize the weak induction as follow. In general, weak induction can start at any integer n sub 0. So let n sub 0 be a fixed integer and let s be a set of integers satisfying the following. N sub 0 is in S, and if an integer k greater than or equal to n sub 0 is in S, then k plus 1 is also in S. So this is basically the same as our weak induction, but the only difference is that the starting point now, instead of 1, is any positive integer n sub 0. So you have the starting point n sub 0, and then the second assumption says that from a starting point, every succeeding integer now is an element of S. So that will mean that S contains all integers greater than or equal to n sub 0. So that's the generalized version of the weak induction. Now, in general, we can do away with our reference of S and we can change mathematical properties or we can denote mathematical properties as statement or propositions of certain set of integers. So how do we do that? So in general, we have the first principle of mathematical induction. Now for an integer n, let's say that P of n is a statement of or a proposition about n. So it's a statement that is dependent on the value of n. And let's say that this proposition satisfies the following. P of n sub 0 is true for some integer n sub 0. And whenever P of k is true for some integer k, P of k plus 1 is also true. Then we conclude that P of n is true or a valid statement for all integer n greater than or equal to n sub 0. So basically what it's telling us is we start with a statement P of n sub 0. So that's your basis for induction. And then the second statement tells us that for any integer k such that P of k is true, then the statement for the next integer is also true. So that means if you have P of n sub 0 to be true, then P of n sub 0 plus 1 is also true. And then the next statement, P of n sub 0 plus 2, must also be true, and so on and so forth. So that tells us that it will be true, or the statement is true for all n greater than or equal to n sub 0. So basically, that's what mathematical induction is. So to simplify the process, this is what you need to follow when you want to prove a statement by mathematical induction. First, you need a basis of induction. You need to verify that a statement P of n is true for some fixed integer n sub 0. So this will be your starting point. Next is the induction hypothesis. You need to assume that the proposition is true for an arbitrary integer k greater than or equal to n sub 0. So this is an assumption. So this is your P of k. So you assume that it is true for an integer k. So that's your inductive hypothesis. Now, to prove induction, you must show that that statement P is also true for k plus 1. So you need to show that P of k plus 1 is also true. So here, you assume this, and for k plus 1, you show that it is true. So once you were able to show that P of k plus 1 is also true, then you can now conclude that the proposition is true for all integer n greater than or equal to n sub 0. Kung saan ka nag-start? So our starting point is n sub 0. So that means that the induction uh, step proved that the proposition is valid from that starting point, n sub 0. So for all n greater than or equal to n sub 0. So an easy way to imagine induction is like a setup of a domino. So let's say you have an infinite number of dominoes stacked together. So there are two important things for the domino fall to succeed. Meaning, first, you need an initial push, and for every succeeding dominoes, if a certain domino, let's say the domino on the kth position fall, then the next domino must also fall. So that's the condition of the domino. So you just have to push the first domino, and then all the rest will follow. Provided that the kth domino or any kth domino that will fall, the next domino will also fall. Because what will happen if it doesn't happen? That means if the inductive step is not true. So if the two dominoes are too far away, then in that particular situation, even if the kth domino fall, then the next domino will not fall. So your series of domino will fail. So that's the importance of the inductive hypothesis. Now, the importance of the basis of induction is it will start your domino. So if you do not push your first domino, then there will be no series of dominoes to fall, right? So that's the importance of the two. Now, it doesn't necessarily mean that you start your push on the first domino. So you can start your push at any starting domino. So you can skip. So that means probably the first few domino will not fall, meaning our formula for the first few integers may not be necessarily true. And you can start your domino effect on any position. So, kung saan mo in-start yung push ng domino, dun magsisimula yung domino effect natin. And that's precisely true for induction as well. So you always have to remember the two important steps of our induction. First, you need a basis for induction, or that's your starting point. So you just have to show that this particular proposition is true for this fixed integer. And then you assume that for any integer greater than the initial integer, or the initial value n sub 0, you assume that the proposition is true for any arbitrary k. And then you show that the same proposition is also true for k plus 1, for the next value k plus 1. Then you conclude that the whole proposition is true from the starting n sub 0 to any integer and greater than or equal to n sub 0. Let's have some example. Given the first few sum, 2 to the 0 is 1, 2 to the 0 plus 2 to the 1 is 3, 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 is 2 to the 2 is 7 rather. Okay, so that means we're just adding up the next 2 to the n, right? So we start with 2 to the 0, you add 2 to the 1, and then you add for the third series of number, you add 2 squared. For the next series of number, you have 2 cubed, and so on. So this is 2, up to 2 cubed is 15. So plus 2 to the 4, 16, 15 plus 16 is 31. So now we want to find the formula for this pattern. So what if in general, we have 2 to the 0, 2 to the 1, 2 to the 2, up to 2 to the n minus 1. So that's the sum of n powers of 2, right? So 2 to the 0, 2 to the 1, 2 to the 2, up to 2 to the n minus 1. So we have n powers of 2 starting from 2 to the 0 up to 2 to the n minus 1. And then after claiming, or after asserting a certain formula, we want to prove the validity of that formula by induction. Now, it's easy to find the pattern for this sum, right? You can just look at the pattern. 1 is actually 2 minus 1, right? But 2 minus 2 is 2 to the 1. So we're adding, where we have 2 to the 0 is the same as 2 to the 1 minus 1. Right? Okay. Now, on the other hand, 3 is 4 minus 1. But 4 can be written as 2 squared minus 1. Let's look at the next pattern, 7. We know that 7 is 8 minus 1. So that's 2 to the 3 minus 1. 15 is 16 minus 1, right? So that's 2 to the 4 minus 1. 31 is 32 minus 1. So that's 2 to the 5 minus 1. And confidently, we can now deduce that eventually, right, this is 2 to the n minus 1. So this is our claim. We claim that the sum of the first n powers of 2, 2 to the 0 up to 2 to the n minus 1 is equal to 2 to the n minus 1. Okay, so that's our claim. So we want to prove our claim using induction. Okay. So how do we do that? So we just have to first have a basis for induction. Second, assume that for an arbitrary k, our claim is true. And then we proceed to showing that it is also true for k plus 1. Okay. So we start with our proof by mathematical induction. So number 1, we need a basis for induction. But we already attained, we actually have several bases for induction. But of course, we want to start with the smallest value of n. So in this case, for n equals 1, right, the left-hand side is equal to 2 to the 0, which is 1. the right hand side is equal to 2 to the 1 minus 1, or that's equal to 1 as well. So since they are equal, therefore P of 1 is true. By the way, our statement is this. Our P of n is a statement of our formula. So that's 2 to the 0 plus 2 to the 1 plus 2 to the 2 and so on. Up to 2 to the n minus 1 is equal to 2 to the n minus 1. That whole statement is our proposition, the formula. All right. Now, the next is to assume, right? We want to assume that the formula holds for an integer k greater than or equal to 1. So let's assume that p of k is true for some k greater than or equal to 1. So k is an integer greater than or equal to 1. The next is to show, we want to show that p of k plus 1 is also true. So how do we show that p of k plus 1 is also true? We want to show that, ano ba yung p of k plus 1? We want to show that 2 to the 0 plus 2 to the 1 plus 2 to the 2 and so on and so forth up to 2 to the n minus 1 plus 2 to the n plus 1 minus 1. So 2 to the n should be equal to, or rather k. So we're using k. So this should be in terms of k. So k minus 1 up to k is equal to, by formula, we want to show that this is equal to 2 to the k minus 1. Or rather, sorry, k plus 1. So this is our p of k. So this is p of k plus 1. So that's what we want to show. We want to show that that statement is true. Meaning the left hand side is equal to the right hand side. So we start with the left hand side. So the left hand side is equal to 2 to the 0 plus 2 to the 1 plus 2 to the 2 and so on up to 2 to the k minus 1 plus 2 to the k. But from our assumption, recall that our assumption is that p of k is true. So from our assumption, the first k powers from 0 to k minus 1 is equal to 2 to the k minus 1. Then we rewrite 2 to the k. Sorry, this should be 2 to the k minus 1 here plus 2 to the k. Now, we add 2 to the k, so that's 2 to the k minus 1. But if we simplify this, we have 2 to the k plus 1 minus 1, which is exactly the right-hand side. So this is already right-hand side. So therefore, we were able to show that p of k plus 1 is also true. By mathematical induction, we conclude that p of k holds or is true for all integer n greater than or equal to our starting point, which is n equals 1. And we are done. There is another version of induction called strong induction. It's called strong induction in the sense that it uses a stronger inductive hypothesis. So let S be a set of positive integers such that 1 is in S, and if k is a positive integer such that 1, 2, and so on up to k is in S. Then k plus 1 is in S. In this case, we conclude that S is the set of natural integers. So, as as we mentioned a while ago, this is called a strong induction in a sense that it's using a stronger inductive hypothesis. Here, instead of just showing k plus 1 by assuming k, we are now showing k plus 1 by assuming that 1, 2, 3 up to k is in S. So we're now using a stronger version of the inductive hypothesis. As with the weak induction, in general, it doesn't necessarily need to start at n equals 1. It can start at any fixed integer n sub 0. So to state this in a more useful form, we call the second principle of mathematical induction. We have for n in the set of integers, let P of n be a statement of or a proposition about n. That satisfies the following. P of n sub 0 is true for a fixed integer n. And whenever P of n sub 0, P of n sub 0 plus 1, P of n sub 0 plus 2, and so on up to P of n sub 0 plus k are true for some integer k, the next proposition P of k plus 1 is also true. Then we conclude that P of n is true for every integer n greater than or equal to n sub 0. This is basically equivalent to the first principle of mathematical induction. The only difference now is that it's using a stronger inductive hypothesis. Now, it's now assumed that it's, instead of just P of n sub 0 plus k to be true, we assume that all the preceding propositions in terms of n sub 0, n sub 0 plus 1, n sub 0 plus 2, and so on up to n sub 0 plus k are true. And then whenever that is true, then the next proposition, P of n sub 0 plus k plus 1 is also true. This should be n sub 0 plus k plus 1. Which is pretty much the same as the case of the first principle of mathematical induction with the additional assumption here. So instead of just assuming P of n sub 0 plus k, we're now assuming all the propositions from the starting point P of n up to the arbitrary point P of n sub 0 plus k. And then we will show that the next proposition at n sub 0 plus k plus 1 is also true. For example, let's consider the Lucas sequence 1, 3, 4, 7, 11, 18, 24, 47, 76, and so on. This is just the same as a Fibonacci sequence. The only difference is that it's starting its first two numbers in the sequence are 1 and 3. So, it can be defined as follow. A sub 1 is 1, A sub 2 is 3, and then all the succeeding terms can be derived by adding the two previous terms. So, A sub n is the sum of A sub n minus 1 and A sub n minus 2. Meaning, if you want to get A sub 3, that's A sub 2 plus A sub 1. If you got if you want to solve a sub 4, so that will be a sub 3 plus a sub 2. So that's 3 plus 4, 7. A sub 5 is a sub 4 plus a sub 3. So 7 plus 4 is 11. So you just have to add the two previous term to get the next term. So 7 plus 11 gives you 18, 11 plus 18 gives you 29, and so on. So what we want to show is that for any integer n, a sub n is less than 7 over 4 to the n. Okay. So here we use the second principle of mathematical induction, which uses a stronger inductive hypothesis. Okay. So how do we do that? First, we need a basis for induction. So we look at the case for A1 and A2. So for n equals 1, we have 1, which we know to be less than 7 over 4 to the 1. So since this is true, then the proposition, this is our proposition, is true for n equals 1. For n equals 2, the proposition is 1, rather 3 is less than 7 over 4 squared. So we know that 7 over 4 is 49 over 16, right? And we know that that's greater than 3. So this is also true. Okay. So we already have a basis. Actually, you just have to compute that for n equals 1. I just wanted to show that it's also true for n equals 2. And you can also check that it's true for n equals 3 and so on. So that's our basis for induction. Now, the next is to uh, provide. So the next is to assume that for k greater than or equal to 3, since our general formula started for n greater than or equal to 3, we want to show that the inequality holds for n equals 1 to up to k. So that's our assumption. So for the inductive hypothesis, we assume that for k greater than or equal to 1, alright, so from a starting point, p of 1, p of 2, p of 3, and so on, up to p of k are true. So we need to show that it also holds for, we need to show, we need to show p of k plus 1 is also true. All right. So how do we show that that statement p of k plus 1 is also true? All right. So this first our assumption means that p of 1, so we've already showed that 1 is less than 7 over 4 to the 1. That's true. Our second assumption, 3 is less than 7 over 4 squared. Our p of 3, so that's the third term. The third term is 4 is less than 7 over 4 raised to 3, and so on, up to a sub k. That is less than 7 over 4 raised to k. So that's our assumption. So our assumption is that all of these statements are true. So now we want to show that our statement a sub k plus 1 less than 7 over 4 raised to k plus 1 is true. So how do we do that? Of course, we start with a sub k plus 1. By formula, a sub k plus 1, right? This is actually equal to, by formula, a sub k plus a sub k minus 1. The two preceding terms. So if we're on the seventh term, we need the sixth and the fifth term. If we're on the k plus 1 term, we need the kth term and the one preceding that, the k minus 1 term. All right. Now, this is now why we need a stronger hypothesis. Because we have two terms, a sub k and a sub k minus 1. So if we use the weaker version where you only assume a certain property to be true only at k, then you cannot conclude if your statement contains another term. But because we have a stronger hypothesis, it is not just true. We assume it to be not just true for k, we also assume it to be true for the rest of the terms smaller than k. So it's also true for k minus 1. It's also true for k equals k minus 2, k equals 3, k equals 2, and so on. So for all k or for all values between 0 to k, lahat ng terms preceding k minus 1, we have an assumption for that property. All right. So because of the strong hypothesis, we can have an assumption. We have an assumption for k and k minus 1. So we can right away say that this is less than 7 over 4 is to k plus 7 over 4 is to k minus 1. So here we use the inductive hypothesis. So let me just factor out, right? Let me just factor out 7 over 4. So you factor out 7 over 4 to the k minus 1. We have 7 over 4 plus 1, right? Okay, but 7 over 4 plus 1 is simply 7 over 4 raised to k minus 1. So here we have 11 over 4. Okay, a few manipulation. 11 over 4 is actually less than, we want this expression to be in terms of 7 over 4, right? Now, observe that 11 over 4 is the same as times 4 over 4. So, that's the same as 44 over 16. Alright, now, 44 over 16 is less than 49 over 16, which is 7 over 4 squared, right? So 11 over 4 is less than 7 over 4 squared. So that means this expression is less than 7 over 4 to the k minus 1. Let's replace 11 over 4 by 7 over 4 squared. So that's definitely less than. But this term here, right? If you look at this term, that's actually equal to 7 over 4 raised to k plus 1. So, what do we have? We have from the beginning, we have a k plus 1, and then this is less than, all right, 7 over 4 raised to k plus 1, which is our statement in k plus 1. So, that means this implies p of k plus 1 is 2. So by assuming that the statement is true for P of 1, P of 2, and so on up to P of K, we were able to show that it is also true for P of K plus 1 by the second principle of mathematical induction. Therefore, P of N holds for all N, right? Either than or equal to. So what's our starting point? So our starting point is 1. And we are done.